Hello, Janaya.
Hi,
How are you?
I'm fine. Okay, here it is. I'm fine. How are you?
I'm doing fine too. How's the class going for you so far? Organic chemistry?
It's it's definitely rough. I think
Mhm.
I just have to take it one chapter at a time and then it'll slowly but surely get better.
Yes, of course, like with a lot of practice as well, like looking at the material before the lecture, during the
Mm-hmm.
lecture, and after lecture, the lecture would definitely help.
Mm-hmm.
And I saw that today you wanted to go over ethers, epoxides, and thiols.
Mm-hmm.
So what we could do, right, is that we could go through like the lecture slides by a
Mm-hmm.
topic, like nomenclature, structure and properties, the reactions of it, and then go through that practice worksheet that you sent. And
Oh
I give
yeah.
you practice problems throughout, or we could work through your homework problems that he assigned you, and then I could teach
Okay.
you the concepts along the way. Which one would you like prefer?
Um, honestly, can we go through homework
Mhm.
problems?
Yeah, of course. We could go through homework problems. So what you could do is you could send it through to me through email or your phone number,
Mm-hmm.
or you could share me your screen on Zoom. Let me allow you to. I think you should be able to share your screen, and then I could help you through it through the homework problems. Mhm.
I don't have my Apple Pencil, so I'm trying to figure out how to draw on the tablet.
Oh, the tablet. Oh, do you have a tablet like an iPad or
Mm-hmm.
like a? Wait, do you have like a pencil with it, like a stylus with it as well for it?
Yeah, I can't find it for some reason. I don't know
Yeah.
where I did with it.
Yeah.
Let's see. Because the
Mhm.
problems that I wanted to go over, I think I sent them to you through the email.
Right,
Let me
and that's the
see.
one with the key, right? Like this one right here. This this
Yes.
this one.
Mm-hmm.
Right, right. Yeah, we could go through these problems, um, and I could walk you through how they got the answer.
Okay.
Okay, so
Let's
let's
see if
get
I have.
yeah,
Yeah, I do not have that other pencil.
yeah. When is this a new iPad? Like, did you get it recently?
No, I just keep losing the.
Let's see, let's see. It's okay. Uh-huh. Okay. So, before we get started with these problems over here, like these are working with epoxides, right? This first question
Mm-hmm.
here. So let's say this is one, this is two, and then this is three right here. So just in general, right? Let's say that we have this epoxide, which is a three-membered ring, where
Mm-hmm.
one of the atoms is the oxygen and then two other atoms are carbons. I think the other name for epoxide is oxyrain, right? And let's say it's going to have a more substituted side and a
Mm-hmm.
less substituted side. So we could say that this carbon on the left right here is the more substituted side. This carbon on the right here is the less substituted side, right? And then we can open up this epoxide in two ways. We can open it up in acidic conditions or in basic conditions, right?
Mm-hmm.
So let's talk about basic conditions first, and then we'll talk about acidic conditions afterwards. So in basic conditions, just think about like negative charges, right? Like
Okay.
alkoxide ions, like OR minus or OH
Mm-hmm.
minus hydroxide ion, right?
Okay.
So if we have, let's say, something like this, I want to do it in the same format as your professor. So let's say we have these reagents right here. I'm gonna do that as the first step, and second step as the acid workup. So whenever you see sodium, do you know what charge is associated with that? Like, if let's say this is an ionic bond, what charge is usually associated with Na, sodium?
A negative charge.
A negative charge? Yeah, so a negative charge usually goes with the sodium, but the sodium itself is positively charged,
Oh yes. Okay.
like a positive ion, meaning that what is attached to it is negative charge. So the negative charge here is the OET, right?
Okay.
But think of the sodium Na as a spectator ion. It's not going to do anything in the reaction. We can basically
Mm-hmm.
ignore that, right? So I'm going to drop the OET in its bond line structure, which looks like this. The ET stands for ethyl, which is two carbons. So this is the O with the negative charge right here, and this is the ET, the two carbons coming out of that oxygen right there. That's the negative
Okay.
OET, right? And would this be a nucleophile or an electrophile? This molecule here.
This will be the nucleophile.
Correct, because of the negative charge right here. And negative charges are nucleophiles, which would attack electrophiles, right?
Mm-hmm.
And we see that this epoxide right here has two carbon atoms that are partial positively charged. This carbon here is partial positively charged, and this carbon here is also partial positively charged, right? And that's because it's
Okay.
attached to this electronegative oxygen atom right here, right? Oxygen is more electronegative than carbon is, so oxygen is gonna
Mm-hmm.
pull or withdraw electrons from that carbon, right?
Mm-hmm.
But in basic conditions, it's gonna do an SN2 reaction. And do you know if in SN2 reactions we prefer to attack the more subside or the less subside?
SN2, I believe it's the more substituted side.
So for SN2, think about steric hindrance. Are you familiar with the term steric
Oh,
hindrance?
yes. Mm-hmm.
Yeah, steric hindrance, meaning that it's like it's gonna prefer to attack the side that has more space, right? Less groups attached to it, less steric
Mm-hmm.
hindrance. Steric hindrance is basically saying like the R groups or like the side groups are bumping
Mm-hmm.
into each other, like they're clashing each other, right?
Okay.
And we don't want that for SN2 because
Mm-hmm.
SN2 reactions need space to attack, right?
Mm-hmm.
So which carbon? Let's say this is carbon A and this is carbon B. Which carbon do you see that has more space?
I
Uh,
think this may be. Oh, that's kind of tricky because they kind of look
mhm.
like they have the same amount of space.
Same amount of space. Right. So let's look at carbon A and carbon B. Ignore this because that's like the same thing attached to A and B.
Mm-hmm.
How many R groups are attached to A? How many groups are attached to A here? Like how many R groups, hydrocarbon chains?
Is it 4?
Yeah. So it is four, right? Which is going to be like 1, 2, 3, 4. But we're gonna ignore the epoxide bonds because you know how this entire structure here is the epoxide right here.
Mm-hmm.
We're gonna ignore this bond and ignore this bond. So if we ignore those two bonds, this carbon is attached to two R groups, which are those two R groups right there,
Oh, okay.
right? Now, if we look at this carbon right here, and we ignore this bond and this bond right here, this carbon is only attached to one R group right there, right?
Okay.
And because this carbon here is only attached to one R group, this carbon
Mm-hmm.
here is the one that has less steric hindrance, right? You can think of it as more space. Since this carbon here only has one R group compared to this carbon, which has two R groups.
Okay.
So that means that this oxygen with the negative charge is going to attack that carbon right there. So when we draw that double-headed arrow, that means that it's an attack
Mm-hmm.
arrow, right?
Okay.
But we can't stop there because if we try to make a new bond between this carbon and oxygen right here, this carbon would break the octet rule, right?
Mm-hmm.
Because this carbon right now has 4 bonds. Well, there's one invisible hydrogen right there that's implied. If
Mm-hmm.
we make a new bond to that oxygen right there, this carbon will have 5 bonds. That's not good. We don't want that,
Mm-hmm.
right? So to conserve the octet rule, we're gonna have to kick out something. And we're gonna kick out this bond right here, right, of the epoxide. And that's how we break open the epoxide. And this bond right here has 2 electrons. We're gonna move those 2 electrons onto that oxygen atom right there, like that.
Oh, okay.
Right? And as a result, we're going to get this right here. So for this first problem, I'm just going to do basic conditions, and then I'm going to do acidic conditions afterwards to show you the full mechanism for that. Okay? We're going to have this oxygen, hydrogen, positive charge. Oh wait, no, that's something else. Oxygen with the negative charge, and then let's say this is going to be oxygen there, and this is going to be that, like that. Okay, does that make sense so far?
Mm-hmm.
This right here is the new bond that we created between the carbon that was attacked and this oxygen atom right here. This is the new bond right there. This oxygen here is no longer attached to this carbon because we broke that bond and gave this oxygen a pair of electrons. That's why it's negatively charged now.
It's negatively charged
Uh-huh.
because we added more electrons to it.
Right, from this bond right here. That bond has 2 electrons, which broke off and went onto the oxygen, giving it a negative charge. Right, because if you think about this oxygen right here, there's 2 invisible pairs of electrons. And this oxygen here with 2 bonds and 2 pairs of electrons is neutral, charge of 0. But if you look at this oxygen right here, this oxygen has 1 single bond and 3 pairs of electrons, right? Giving that oxygen a -1 charge. Are you familiar with calculating formal charges?
Yes.
Right. Okay. So now once we know that that oxygen is negative charge, we now bring in the second step of H3O plus acid,
Okay.
right? And what do you think that acid is gonna do to this molecule here?
I think the is it going to attach a hydrogen to it?
Yes, it's gonna attach a hydrogen to the oxygen, right? But be careful here of how we draw the arrows in the mechanism, right? A lot of
Okay.
students, they would draw the hydrogen going onto the oxygen like that directly, but that's wrong. We don't do that, right? Because when we draw arrows like that, it's attacking something, right? So that means that a negative charge is gonna go towards something positive, towards something partial positive or fully positively charged, right? So this oxygen with the negative charge here is actually gonna use one of its pairs of electrons to grab that hydrogen right there, to take a hydrogen from the H3O plus acid, like that, right? And because this hydrogen is being grabbed, this bond right here between the hydrogen being grabbed and oxygen is gonna break off and go onto that oxygen right there, giving that oxygen a pair of electrons, right?
Okay.
And that's gonna lead us to our final product here, where we have our neutral alcohol, OH, which is this right here. And this right here is the leaving group, which is gonna leave as water, H2O. And notice how before this oxygen here had a positive charge, but now it is now neutral because it gained a pair of electrons.
Okay.
Right.
So it's now neutral because it gained a pair.
Right. Okay. So an important thing here is that in basic conditions, we attack the less substituted carbon of the epoxide. Right? And when we break it open, this is gonna be anti-addition. Right? Or let's say it's gonna invert stereochemistry, but not anti-addition. Let's say think of it like a backside attack, right? Backside attack of SN2, where it inverts the stereochemistry. So to make sense of that, you notice how this bond here is going down relative to this single bond right here. Like this bond is going down. This bond here is staying up. They're anti to each other. They're facing opposite directions. And that's very important. We don't want them in the same direction at all.
Okay.
And that's because if you look at the previous molecule, these 2 bonds here are going up, right? But if you look at the nucleophile, when it attacks this carbon in the SN2 like fashion, backside attack, it's gonna invert this bond that's going up to down, right? So this up bond is gonna be inverted to down, like that, right?
Oh, okay. I think I see it a little bit.
Right. And this up bond right here is gonna stay up because nothing touched this carbon. You know how nothing is attacking that carbon right there? Because nothing is touching that carbon, nothing is attacking that carbon, this bond right here will stay up. Nothing changes that direction of the bond. But if you look at this carbon right here, this bond here that was going up is now down because we invert the stereochemistry. We flip-flop it. We do a backside attack on that because we attack this carbon right here.
Okay. So the backside attack led to inversion.
Led to inversion, right. Backside attack led to inversion for SN2 reaction. Correct.
Okay.
So now that was basic conditions. Let's move on to acidic conditions, right? So let's use the same epoxide. So let's say this is the epoxide right here, and we're gonna use the same epoxide right here. And now in acidic conditions, we're gonna use ethanol, which is ETOH, and in acidic conditions, H2SO4. Right? That's the most common acidic catalyst that you're gonna see. Okay?
H2SO.
Mm-hmm. So H2SO4 is a very strong acid. When you have a very strong acid, you're gonna find the most basic atom. What atom of this molecule here do you think is the most basic atom that's gonna get protonated, that's gonna grab the hydrogen from the acid?
Would it be the get protonated?
Uh-huh. Yeah, which one has electrons that it could use to grab a hydrogen?
I think the oxygen right there.
Correct. Yes, the oxygen of the epoxide. And to draw the mechanism, I'm gonna draw out the H2SO4 in this form right here.
Okay.
Right. And that's because we want to see directly that this oxygen here is going to use one of its pairs of electrons to attack and grab that hydrogen like that. Right? Meaning that this bond right here between the hydrogen being grabbed and oxygen is going to break off and go onto the oxygen right there, giving that oxygen a pair of electrons. Right? So after that, we're going to get this intermediate as a result. Okay, where notice how this oxygen here now has 3 bonds, 1, 2, 3, because it grabbed a hydrogen. Before it had 2 pairs of electrons, right? 1, 2, but now it only has 1 pair of electrons because it used one of its pairs of electrons to make that new bond right there. Like this set of electrons is this set of electrons right here, right? Now, the charge of this oxygen here, are you familiar with the charge of this oxygen that has 3 bonds and 1 pair of electrons? Like, what would be the charge? Like, neutral, positive 1 charge, negative 1 charge?
Would this be positive charge?
Yes, this would be positive charge, right? So oxygen with 2 bonds and 2 pairs of electrons, neutral. Oxygen with 1 bond and 3 pairs of electrons, negative 1 charge. Oxygen with 3 bonds and 1 pair of electrons, positive charge, like that.
Okay.
Right? So now, think of this.
Hey. Yeah, I'm in tutoring. I wish I was Yes.
Oh, hey, sorry, don't interrupt.
No, it's fine. No worries.
It's for organic. Cause this is tough. We're doing ethers and epoxides right now, but it's pretty basic stuff right now. But it's getting rough. Yeah, it's getting rough. Yeah, I know. Yes, I swear. Yeah. Okay, see you later. Sorry about that.
No, it's fine. It's fine. What major are you?
I'm a neuroscience major.
Oh, neuroscience major. Wow. What year? Uni?
3rd year.
3rd year. Oh, wow. Okay, okay. 2 more years. Let's go.
I know, and hopefully I can just get chemistry out the way.
Yeah, I know. Wait, is this your last chemistry class? Okay, let's get let's get through this class together. Yeah. So for this epoxide right here, this oxygen with the positive charge right here is a good leaving group, right? So that means that these carbons here are going to be the electrophiles. And have you learned about carbocation stability? Like, are you familiar with these carbocation structures here, where we have a carbon with a positive charge? Which one would be the most stable carbocation?
Is it the tertiary?
Yes.
Or
tertiary carbocation is the most stable because it has more R groups around it, more hyperconjugation, right? Compared to the secondary carbocation, compared to the primary carbocation. So if we were to, let's say, break this bond and go to that oxygen right there, we would have, let's say, this carbocation right here, right? But if we were to break this bond and go to that oxygen right there, we would have this carbocation right here. And which carbocation do you see that is more stable? Carbocation A or carbocation B?
Carbocation A.
Yeah, carbocation A, because it's more substituted. right?
Mm-hmm.
So that's why in acidic conditions, let's draw out the ethanol, which looks like this in bond line structure. If we want to get to the more stable carbocation intermediate, where do you think this ethanol is going to attack? A or B? Which one led to the more stable carbocation intermediate? Right? Like imagine like these bonds are no longer there, and imagine a positive charge here versus a positive charge here. Right? We said earlier that it's gonna be A, this one right here, right?
Mm-hmm.
Because it's more substituted. And
Oh,
right.
okay.
And because of that, that's why in acidic conditions, we attack the more substituted carbon right there.
Okay.
Breaking this bond, going outside of oxygen, leading us to this intermediate right here. Right? So drawing this can be difficult because let's say this bond here is the reference bond. You know how we're attacking this carbon right here and we're breaking this bond that's going up right now?
Mm-hmm.
What direction would this bond now be if we're doing a backside attack?
The bond would be pointing down now?
Down now, correct. Which is why I'm gonna draw the new bond going down like this. That's why I'm not drawing the bond going up like that. Right?
Okay.
I'm drawing the bond going down,
Excellent.
which is gonna be attached to this oxygen, and that oxygen is attached to this ethyl group and the hydrogen like that. And like we said earlier, oxygen with 3 bonds, 1, 2, 3, and a pair of electrons is going to be positively charged like that. Okay. And then this is going to be the dashed methyl. This is going to be the wedged ethyl. This is going to be the wedged isopropyl. And this bond right here is going to stay up because nothing touched that carbon, which is attached to this alcohol, OH. Before, this oxygen was positively charged, but now it's neutral because it gained a pair of electrons from this bond right here. Right. And if I'm going too fast, let me know. And this is also being recorded, so I'll send you the recording afterwards.
Okay, thank you. So I don't have
too.
to write it down.
Yeah,
Or
right,
keep.
right. Mm-hmm. Yeah, right. Because like I know I could like go too fast, but just let me know if you have any questions as well. Right. And I'll send you these like this PDF for you to review as well. Okay. Now, once we have this, the last step of the mechanism is to use the conjugate base, which is HSO4 minus that we formed in the very first step, to deprotonate this positively charged oxygen right here, which will lead us to this final answer right here. Oxygen, ethyl, isopropyl, OH, like that. So that's going to be the final answer for epoxide opening in acidic conditions. The big difference between acidic conditions and basic conditions would be what carbon the nucleophile attacks. In basic conditions, we attack the less sub carbon. In acidic conditions, we attack the more sub position.
Okay.
Right? But in both conditions, we do a backside attack. We invert stereochemistry in both conditions. Right? Okay, that's good. So now let's take a look at this problem over here. We have an epoxide, which is that structure right there. And based on the reagents, do you think we are in acidic conditions or basic conditions?
Acidic conditions?
Acidic conditions, correct. Because we have this strong acid here, this H2SO4. And because we are in acidic conditions, where do you think this nucleophile is going to attack? The more sub position or the less sub position?
The less substituted?
Wait, so if we look back at this mechanism right here, in acidic conditions, we're going to attack the more substituted position right here.
Okay.
Right?
More substituted.
The reason why is because we want to get the more stable carbocation intermediate, right? Because think of this positive charge oxygen here as the good leaving group, which like if we kick it out, we want to form the more stable carbocation intermediate, which is the more substituted position, right? In basic conditions, however, we want to get the less substituted position, the less substituted carbon, because we're trying to get less steric hindrance for SN2, right? Okay, and let's say this is carbon A and this is carbon B. Which carbon is more substituted?
the carbon A.
Yep, the carbon A, correct. So when you draw out the product, right, this is very important. Let's draw out that structure right there. At carbon A, that's going to be attached to this nucleophile here, right? So we could draw a new bond coming out of it, which is attached to this oxygen right there. This right here is the new bond. This oxygen here is attached to a CH3, a methyl group. So you could draw that bond coming out and write Me for methyl group. It's also attached to a hydrogen, which is this hydrogen right here. But we know in the mechanism, right, that hydrogen is going to get deprotonated by the HSO4 minus and make this overall structure neutral. Since this is not a mechanism problem, we could just get straight to the final product there quickly, like that. Right. Now, another important thing here is that because this bond here is going down, where do you think this bond is going to go if it's going to be inverted, like anti to this bond?
Would we have to do a wedge drawing?
Yeah, so we don't have to do wedges or dashes here because they didn't give us any wedges or dashes here, so we wouldn't know, right? But what we can do is that we can make the other bond go up if this bond here is going down, like that, right?
Okay.
So if you're not given wedges or dashes, you can still show anti or like opposite direction in reference to a bond. And our reference bond is going to be this bond right here. That's our reference bond, right?
Okay.
Since this bond is going down, this bond has to go up, right?
Okay.
Yeah. And that bond right there is going to be attached to this OH right there, alcohol right there, like that. Okay. Do you know where this alcohol came from? This OH came from?
Did it come from the acid?
So this oxygen here is going to come from this oxygen of the epoxide right there, like that, right? But the acid hydrogen, which is like this H right here, that is gonna come from the acid, right? Like this hydrogen here is from the acid. And we can look back at the mechanism that we did over here in acidic conditions, right? Notice how the very first step of the mechanism is that the oxygen grabs a hydrogen from the acid. Like, let's say this is the hydrogen of the acid right here, H2SO4. Right? That's where this oxygen gains its hydrogen, gains its proton, right?
Okay, I think I see what you're saying. It looks like the oxygen from the starting material gained another carbon.
Gained another carbon. Let's see here.
Yeah,
so,
right there.
Let's see, 1, 2, 3, 4, 5, 6. Yeah. So, is it this carbon right here that you see is extra? That carbon right there is carbon B. That carbon right there.
Oh, okay. Okay.
Right. And then this OMe structure right here came from this OMe structure right here, OCH3 group right there.
Okay.
And then this OH structure here is the OH from the epoxide and hydrogen and acid.
Okay.
Right. The most important thing here, like there's two most important things here. The OMe group or the OR group has to be on the moist subposition, which is this carbon right here, because we're in acidic conditions, right? And then that means the OH has to be on the opposite side. And then we have to make sure that they're anti to each other, they're opposite directions from each other, like that. Right. So this is either the acceptable answer. On the key, your professor put this, which is the same thing, right? Like let's say this is that right there. He put OMe going up, and he put OH going down. They're still the same thing because OMe is still on the more subside, and then these two bonds here are opposite to each other, anti to each other, like that.
Okay.
Right. It's still the same thing. Right. Okay. So now, once we have that, this is going to go back to organic chemistry 1. Does this set of reagents look familiar to you? Chromium oxide, acidic conditions with.
Is this? This is not hydroboration oxidation. This is acid catalyzed,
You're
I
thinking of
think.
alkene reactions. This might help. Let's say you have a primary alcohol like this, and there's going to be two oxidizing agents. One is going to be PCC, and one is going to be something called Jones reagent.
Yes, this does look familiar, but I cannot remember what we called that.
Right. So this is an oxidation reaction, right?
Oh, okay.
Oxidation.
Yeah.
Right. And in oxidation reactions, what they're gonna do is they're gonna add bonds to oxygen, right? Oxidation, add
Okay.
bonds to oxygen. That's going to be shown here. If we look at this carbon right here, that carbon has one bond to oxygen and two bonds to hydrogen, right? But these are typically invisible, but I'm gonna draw them out to show you the reaction here, right?
Okay.
So you can think of oxidation as the addition of bonds to oxygen or the removal of bonds to hydrogen, right?
Okay.
Because to add a bond to oxygen, you have to trade a bond with hydrogen, right?
Okay.
So PCC here is going to be considered a weak oxidizing agent. CrO3, H2SO4 and acetone here, that overall reagent is going to be considered a strong oxidizing agent. So this weak oxidizing agent here is going to convert this primary alcohol into an aldehyde. So let's say we have this pink carbon right there. It's now going to be attached to a carbonyl, right? A carbonyl is a carbon double bond oxygen and a hydrogen. So notice how this pink carbon here now has two bonds to oxygen. 1, 2. Two bonds to oxygen like that. And it only has one bond to hydrogen. So what we did is that we traded one bond to hydrogen with one bond of oxygen. So we oxidized this primary alcohol into an aldehyde.
Yes. Okay. I do remember alcohol to aldehyde.
Right? With PCC, the weak oxidizing agent. But if you were to use a strong oxidizing agent, like the one with chromium, Cr, you're gonna fully oxidize that down into something else, which is going to be, let's say this is the pink carbon. We're gonna replace all of the hydrogen atoms to oxygen, right? Now this carbon here has 3 bonds to oxygen, 1, 2, 3, and no bonds to hydrogen, 0 bonds to hydrogen. We completely traded these 2 bonds to hydrogen with 2 bonds to oxygen like that.
So we went from a carboxylic acid.
Yes, we went from a primary alcohol to a carboxylic acid.
Okay.
Right. Okay. Okay. Does that make sense so far, Janaya? Okay,
Yes.
that's good. So now, if we look at this right here is a primary alcohol because this alcohol here is on a carbon that's attached to only one other R group, one other carbon. Right? So if we use the strong oxidizing agent, what would this primary alcohol turn into if we use the strong oxidizing agent?
Should turn it to a carboxylic acid.
Yes, carboxylic acid, correct. So the answer for this right here would be like this. So copy and paste everything else, turn the primary alcohol into a carboxylic acid. The ether here, right? The ether meaning that there's an oxygen in between 2 R groups. This is the ether, stays stationary. Nothing happens to that ether.
Okay.
Right. Okay.
So for problems, because this seems like, I think our exam will be a lot like this is just getting the structures down.
Right, getting the structures down and also knowing the reactions because this reaction here is definitely on the notes that you sent me, right? But this reaction here is most likely from Organic Chemistry 1. Like this is not the ether presentation that you sent me. This is from like probably something from Organic Chemistry 1.
Okay.
Right. Yeah. And a tip that I have for you for like these reactions is like know what functional group you are working with. In this case, it's the epoxide. Know the reagents and see how they react and what they form, right? And also understanding the mechanism. Like, you know how before we worked through this problem here, I showed you the mechanism, like in detail,
Mm-hmm.
step by step in different conditions. That would also help. Like, instead of just like trying to memorize,
Yeah.
like A plus B makes C, because
Mm-hmm.
like a lot of these right here would be different. Like the way that he draws it on the exam is different. But if you understand the
Mm-hmm.
mechanism behind the scenes, you could work through it. Like everything else is a distraction. Like find what is the most important thing, which is specifically this epoxide, this nucleophile in acidic conditions, and then you know that it's gonna attack on the more subside, and they're anti to each
Mm-hmm.
other. This cyclohexyl group is a distraction, right? Like it could be something else. It could be like a terbutyl group. It could be a propyl group, like whatever, right? It could be different for the
Mm-hmm.
exam. Yeah. Okay. Okay. So now if you look at problem number 2, we have the same structure as problem number 1, but in different conditions.
Yes. We are in basic conditions now.
Yes, basic conditions now, correct. Because we see sodium is positively charged, making this OMe negatively charged, right? So this methoxide group, which is like OMe negative charge, where do you think it's going to attack? The more subcarbon of the epoxide or the less subcarbon of the epoxide?
Basic conditions are the less substituted.
Less substituted side, correct. And since this is not asking for the mechanism, you don't do the mechanism. Do it if it helps you, but like to
Mm-hmm.
save time on the exam, you could
Mm-hmm.
draw out the product like quickly, right?
Mm-hmm.
So what I would do to draw out the product quickly here is draw out that distraction that doesn't be that is not affected at all. This is the epoxide base. We know that because we're attacking the less subside, which is this carbon right here, we're gonna add the OMe on that side. OMe, like that, on the less subcarbon.
Yes.
Meaning that the more subcarbon is going to have the OH, like that.
Is this considered breaking the ring?
Yeah, this is considered breaking the epoxide ring, like we went
Okay.
over in this mechanism right here, in basic conditions right here. Like that's this
Okay.
reaction right here, right? Okay. Okay. So this next reaction here might be organic chemistry 1, like the end of organic chemistry 1 with alkenes. Like, when did you start learning alkenes? Like, this semester or last semester?
Last semester.
Last semester, alkenes. Okay.
Mm-hmm.
So this might be a blur. But do you know what would happen if you have, like, let's say this tertiary alcohol reacting with acid and heat?
I believe do we it's not a workup step, but is it do we end up with water?
With water? Yes, you will end up with water as a side product, right? But the major organic product is going to do an E1 reaction. It's gonna make an alkene.
Oh, okay.
Yeah. So before we go over that, I'll give you a review of how that works here. Right. And this is called dehydration reaction. Dehydration of alcohol. Right. Dehydration of alcohol. Are these the homework problems that he posts like online for you to try out?
Those problems are usually I think these are the class problems we usually go over. Like a majority of our lecture is going over practice problems instead of really describing the material. Where before coming to lecture, we're supposed to watch these videos and then go to lecture and do practice problems.
I saw your syllabus. I was like, this is interesting format. Like I've never seen a class that's formatted this way before. How do you like it?
Yeah, it's honestly tough because our averages are pretty low in the class, and I think it is because of how the format is.
Is the average below 70?
Oh yeah. I'm thinking 40s and 50s.
40s and 50 averages.
Yeah, on exams. So I feel like they should change the format if that's the average.
Yeah, I know it should, but that's like unfortunately like kind of common like for organic chemistry classes. Like
I heard,
the
yeah.
averages like are extremely low, like 40 to 60s.
Yeah.
Right. Dang. Okay. But at least there's a curve, or hopefully there's a curve. And
yeah,
the grade
that's the good
cutoff
part
is,
about
like,
it.
lower, right?
Mm-hmm.
Okay. So dehydration of alcohol. on our reactant starting material, we have an alcohol, a secondary alcohol specifically because this carbon here is attached to two R groups, right? One, two carbon atoms.
Okay.
We're gonna react this with acid and heat. What do you think the acid is gonna do to this alcohol here?
Will it pronate it?
Yes, it's gonna protonate the OH. So to draw out the mechanism, this oxygen here on the alcohol has two pairs of electrons. It's gonna use one of its pairs of electrons to grab that H. The bond between the H being grabbed and oxygen right there, there's two electrons there. Those two electrons of that bond is gonna break off onto that oxygen like that, forming the water molecule, H2O.
Okay.
And then the intermediate is going to have this O, and I could draw it out like this to make it more clear, right? Before, this oxygen had two pairs of electrons, but now it has one pair of electrons because the other pair became this bond that grabbed this hydrogen right there of the H3O plus. And like we said earlier, this oxygen with three bonds and a pair of electrons is going to be positively charged like that. Now, think of this entire water structure here, or because it's attached to an R group, the oxonium ion, that's a good leaving group. Good leaving group. Right? Okay. So now, with this good leaving group right here, let's just make it leave. Right? Let's make this bond right here, attaching this carbon and oxygen together, break off and go onto the oxygen right there, giving water, H2O. And what charge do you think this carbon will have if it lost the bond?
This will be a negative or positive charge carbon, I think.
Yeah, positive charge carbon, right? Because it's losing electrons, and if it's losing electrons, it's losing a negative charge, right? So so that means it's gonna be positively charged. Another way you could think about it is that this carbon here previously had 4 bonds. 1, 2, 3, 4. But because we kicked out this good leaving group, we lost the bond. Now this carbon here only has 3 bonds. 1, 2, 3. Right?
Okay.
And a carbon with 3 bonds has missing 2 electrons, so that carbon is gonna be positively charged like that.
Okay.
Okay, so now from here, because we are given heat, that's gonna favor the E1 reaction, meaning that we're gonna create the more substituted alkene. Okay, so to do that, let's say this carbocation here is the alpha carbon, and the carbons like right next to it, adjacent to it, are the beta carbons. I'm gonna draw out the beta hydrogens for each beta carbon. Let's say this is hydrogen A and this is hydrogen B. Which beta hydrogen is more substituted? Which beta hydrogen has more R groups surrounding it?
I believe A does.
A does, correct. So that's the one that the base, in this case water, is going to grab, and the bond between HA and carbon right there is going to make a double bond right here between the alpha and beta carbon.
Okay.
Like that, right? And that's going to give us this alkene right here. But this right here that I just drew out is the minor product, so let's not draw that as the major product. That's because the major product would be this right here, right? The trans alkene. The trans alkene is major over the cis alkene. Are you familiar with trans versus cis alkenes?
Yes, but I don't know why they're one's favored over the other one.
Right. So the cis alkene means that the 2 R groups on the alkene are on the same side. Trans meaning that they're opposite from each other, right? And cis is minor because it's less stable. The 2 groups that are on the same side, they're gonna bump into each other. They're gonna clash into each other. That increases steric hindrance, and we don't like that. We don't want steric hindrance.
Okay.
Right. Steric hindrance is like the groups bumping or clashing into each other, which like is very unstable for the system. Okay. trans alkene avoids that steric hindrance because they're opposite from each other. They're facing away from each other. Like that, right? Okay. Okay. So I'm gonna give a random practice problem here, and I'm gonna show you how to predict the product quickly without having to draw out the whole entire mechanism. So let's say we have this alcohol right here, reacting with the same reagents, H3O plus, and heat. Okay, so here's how you can predict the product quickly. If you see an alcohol with acid and heat, know that you're gonna make an alkene, the most substituted alkene that you can make. And the possible alkenes that you can make are either gonna be here or here, right? Getting rid of the alcohol. So if I were to make an alkene there, that would look like that. If I were to make an alkene down there, it would look like that. Which alkene looks more stable to you? Which alkene looks more substituted to you?
The one with the double bond higher.
On let's say A or B? A or B?
A.
A, right? So A right here, has only two R groups, right? Like it's gonna be attached to this R group and this R group because this carbon is attached to one hydrogen, this carbon is attached to one hydrogen right there, right? But if you look at B, this alkene is tri-substituted, right? Because it's attached to three R groups. 1, 2, 3, and this carbon here only has one hydrogen, like that, right? So let me make this more clear by showing you the alkene. This is unsubstituted. There's no R groups attached to that alkene. This is gonna be mono-substituted. There's one R group, and there's three di-substituted alkenes. There's the cis, there's the geminal, there's the trans, there's the tri, okay, and then this is the tetra-substituted one right here. So this is gonna be unsubstituted because there's no R groups. This is mono substituted. These three here are di substituted because there's two R groups attached to the alkene. 1, 2, 1, 2, 1, 2. This one here is cis. This one here is geminal. This one here is trans. This right here is tri substituted, and this right here is tetra substituted. And the stability goes like this. The more substituted the alkene, the more stable it is. So tetra substituted here is the most stable, then tri substituted, then di substituted is more stable than mono. Mono is more stable than unsubstituted. And specifically, the trans alkene is more stable than the cis and geminal alkene. The cis and geminal alkene are gonna have relative stability because notice how those two R groups are gonna clash into each other the same way, like that. They're gonna have the same steric hindrance, right? So the more substituted the alkene, the more stable it is, right? So we see that we can either form this alkene or this alkene, getting rid of that OH because we know the OH is going to leave as a leaving group. So we can either get this product or we can get this product. And what kind of alkene is this right here? Is it unsubstituted, mono, di, tri, or tetra?
I think this is is this di-substituted?
Di-substituted, that's correct. And the way that you can figure that out is like find the carbons of the alkene, which are these two carbons right there. Those two carbons are double bonded to each other, right? And then see how many branches you see coming off of it. We see only 2 branches. 1, 2.
Okay.
Right?
Okay.
If you look at the other one right here, these are the 2 carbons that are double bonded to each other. Those are the 2 carbons that are the alkene carbons. If you see how many branches are coming out of that, there's 1, 2, 3. So that makes this tri-substituted. 3 groups coming off of that, right? And because of that, this right here is our major product.
Oh, nice. Okay.
Right? And if you were to predict the product, I wouldn't even draw that because that's the minor product, and they would look for the major product instead, right? Okay. Okay. So now, if we go back here, right? You notice how we have this alcohol here reacting with acid and heat. this OH we know is gonna go away because once it gets protonated, it becomes like a good leaving group water, and then we know that. Where do you think the double bond is gonna be? Like there's two possibilities where the double bond is gonna be. Well, actually three in this case, but like, two unique ones. Like how would you predict the alkene, the possible alkenes?
Um, I would usually. I always think about the OH. Maybe the alkene was somewhere go in the ring somewhere.
Right. So we could say that alkene could go like right there,
Mm-hmm.
right? Right next to the OH. It can't be here, right? Of
Mm-hmm.
the ring because it's not next to the OH. Like the alkene has to be attached to a carbon that was attached to the OH. So it has to
Mm-hmm.
be either here or here, right? But it doesn't really make a difference because this is symmetrical, right? Like if let's say there was an isopropyl group here, then it would be different. Like there
Mm-hmm.
would be different alkenes. Like this alkene would be different than the alkene. But because they're symmetrical, there's nothing there. Both are equal. So I'm gonna draw out that one alkene right there like that with OMe. And then the other possible alkene is if we were to make the alkene right here, outside the ring,
Oh yes. Okay.
right? Because it's still attached to this carbon right here.
Mm-hmm.
That had the OH, right? Okay. Now this is interesting because what do you think is the major product?
Let's see.
Right. So
Maybe that one, the second one, or the last one you just drew.
this one right here.
Yes,
And what's your reasoning behind that? That
I
choice?
think because it's bonded to the ring and making it more substituted than the one that's in the ring.
So if you look at the one inside the ring,
Mm-hmm.
how many groups are coming off? How many carbon groups are coming off of the alkene?
Let's see. It looks like three.
Three, correct. Right. So let's say these are the two carbons right here. 1, 2, 3. Now, if we look at the one on the right, let's say these are the pink ones. But actually, let's do purple. Purple ones. How many carbon atoms are coming out of the alkene?
It looks like it's two.
2, correct. 1, 2. This right here is not carbon, so we don't count that. So
Oh yes. Okay.
So based on that, which one is more stable? Which one is more substituted with carbons?
The green one.
Yep, that's gonna be our major product. And this is gonna be our minor product. Right? That's well, I go, do you go to your, does your professor have office hours, Janaya?
Yes, he has
Yes.
office hours during my class time.
During your class time, okay. Are you comfortable with asking him questions?
I try to because
You try
sometimes
to?
he'll
Yeah.
look at me and say, "Why don't
Yeah.
you know this by now?"
Oh yeah. No, don't worry, with that. Because like I would argue that because this is what he put in his key, but I would argue that this is the major product, and because of a different reasoning. Have you heard of resonance? Like, are you familiar with the resonance?
Yes.
Right.
Mm-hmm.
Okay, so I'm gonna erase these right here. Like, and this is something you could ask him in office hours because I'm actually curious on like why he put that as major and this as minor, right? So we see this alkene right here, and this oxygen here has 2 pairs of electrons. Can you see which one of these structures can do resonance based on looking at it?
I think it is the purple one that can do resonance.
Correct. Because the oxygen with the pairs of electrons, right? Let's say one of the pairs of electrons goes to make a double bond right here, shifting this double bond onto that carbon, giving that carbon a pair of electrons. So I would draw out the resonance structure out like this. OMe, oxygen with 3 bonds and pair of electrons, positive charge. This carbon here gained a pair of electrons, so it's going to be negatively charged. So these right here are resonance sides of each other, and to confirm, make sure the overall charge is equal. The overall charge of this structure is 0. The overall charge of this is also 0, so that checks out. Because positive 1 minus 1 equals 0. Right?
Okay.
So, because of the resonance here, I would argue that this is the major product because they're able to do resonance. Whereas this right here is not able to do resonance since there's a sp3 roadblock in the way, which is this carbon right here, right? Like we can't make a double bond right there because like that's an sp3 carbon. We can't like shift double bonds or charges around like that. Right? That sp3 carbon right there with 4 bonds is blocking resonance, right? Okay, so that's something you could ask your professor, like why would like this right here, does the resonance make a factor, and is resonance a factor in determining major structure here, like that, right? Okay, but on the key, this is what he says, and that's because of the substitution factor.
Okay.
Right. Okay. 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 So now for the next one here, are you familiar with the reagent MCPBA and what that would do with the epoxide? Like what functional group that would create?
Didn't know this too. I believe it does create an alcohol.
So an alcohol, let's see here. An alcohol from an alkene, that would be with acid and water, right?
Okay.
So for this one here, this is a new reaction from this chapter, the ether and the epoxide reaction. When you see MCPBA with alkene, think of creating epoxides.
Okay.
Epoxide, right? Okay, and the epoxide, right, is gonna come from the alkene. So let's say these carbons here are the alkene carbons. Those are gonna be the base of the epoxide. So let's say this is that carbon right there. Those 2 carbons that I just circled in red is gonna be the base of that epoxide right there, like that.
Okay.
Right.
Okay.
Okay. Okay. So now for the next reaction here, we're gonna react it with NaCN. Is this acidic conditions or basic conditions? Like what charges are gonna be relevant here? Like what charge is the nucleophile?
I believe this is acidic conditions.
Acidic conditions. So do you see any strong acid here, like H3O plus, H2SO4?
No.
No, right. So this is not going to be in acidic conditions. When you see sodium, that's positive charge. When you see CN, that's negative charge. So CN minus here, whenever you see anything that's negative charge, right, ignore the sodium. Sodium's not going to do anything. When you see anything that's negative charge, that's basic conditions. Basic.
Okay.
Right. Like OR minus, OH minus, in this case, it's going to be CN minus. And because we have a minus charge and negative charge, we're going to be in basic conditions. Okay. And do you remember from the beginning of the session, in basic conditions, would we attack the more sub side of the epoxide or the less sub side of the epoxide?
The less sub-side?
The less sub side, right. Which is going to be this carbon right here. Less substituted. There's less R groups coming out of that carbon.
Okay.
Right. Does that make sense? Like why this is less sub and this is more sub? Right? Because there's more groups coming out of that carbon, there's like less groups coming out of this carbon right here.
Okay.
So to predict the product quickly here, let's just draw that out. This is the base right here. The CN is gonna go right there. And this bond here is gonna be attached to the OH, but do you think the OH is gonna go up or down if the CN is already down like that?
Up.
Up, right, because it's gonna have to be inverted. It's gonna have to be anti to each other like that.
Okay.
Right. But in this situation here, because we don't have an acid workup, right? It's not gonna be neutral OH. It's gonna be negative charge O minus. Right. And that's because if you think about the mechanism here, the CN minus, when it attacks that less subcarbon, this bond breaks and goes onto that oxygen, giving that oxygen a negative charge, O minus. And then because we don't have like the second step H3O plus, we can't protonate this O minus into the neutral OH. He didn't give us the second step H3O plus, so our final answer here would be stopped at this negative charge O minus right there, like that. Right?
And then could you briefly go over the H3O plus? What did you mean by that?
Yeah. So once we have this intermediate right here, when we open up the epoxide, does that make sense so far on how we got this tetrahedral? I mean, this intermediate right here, where we have a CN on the left subside and then the O minus on this side right here, like where this negative charge
Yes.
came from. This is the final answer. Right?
Okay.
If he were to, let's say that's the first step, and then the second step is H3O plus or acid, right? What do you think that would do to this molecule when I have this H3O plus floating around and this molecule floating around? What would they do with each other?
They would with the oxygen grab a hydrogen from it?
Correct. Oxygen will grab the hydrogen. The bond between the hydrogen being grabbed and oxygen right there is going to break off and go make a water molecule like that, giving us this as our final answer, where we have an OH, a neutral OH, not an O minus anymore, but a neutral OH because they grab the hydrogen from the H2O plus. The CN stays the same. And that would be the final answer if your professor put that as a second step. Acid right there. But because that's not there, he didn't put it there, we stop here, which is that final answer right there.
Okay.
Right. Okay. And if you look at the previous example here, you know how we were in basic conditions right here? He didn't put acid breakup. Like there's no second step H3O plus. The reason why it's neutral here, right, is because the acid source, the proton source, is not H3O plus, but the proton source is going to be this methanol right there, right?
Okay.
So when you see the intermediate right here, which is I'm going to skip straight through it, we have the O minus right here. That O minus is going to get protonated by this methanol, like that.
Okay.
So
yes.
grab that, kick out the OMe to create this neutral structure there, right?
Okay.
But there's no proton source here. There's no source that has a proton for to protonate this O minus like that.
So it's just O minus for the final product.
Right. Correct. Okay. Yeah. When is your exam on this material, Janaya?
The written portion is next Wednesday.
There's two portions. What?
Yeah, there's a it's a multiple choice portion and then a written portion. I think we had 2 hours for it, so I'm assuming it's probably gonna be a living nightmare if they give us that much time.
Yeah. Oh my gosh. Dang. And is this on ethers, epoxides, and thiols? Is there anything else, like any other topics covered on that exam?
Yes, I have a whole big list.
I saw that on the syllabus, right? Yeah.
We have I think aromatic rings. We're learning that tomorrow, but that's on our exam on next week.
On next Wednesday, the aromatic rings like benzenes and stuff like that?
Yes.
Oh my gosh.
Yes.
Dang. And did he say like these worksheets and practice are going to be similar to his exams, or he didn't mention anything about it?
Yeah, he says he highly recommends we go through the worksheets and practice exams because they're roughly what we'll see on the exam. He said the exam would be just a little more trickier than these, but
what?
yeah.
Oh no.
But he said to go over these.
Right. When we go over these, like I try to like give you different scenarios, different problems, just in case they show up on the exam, so you can understand it and apply it on the exam, not just like go straight through the like exam problem itself. Like I want to expand it upon it. And hopefully this helps. I will send you the recording and notes to this after. And I do want to give you a free one-on-one session if you're down to give me like a video testimonial if you're interested.
Okay.
Like a 30 to 60-second video testimonial.
Okay.
Right. Okay, yeah. And then we can schedule that. Like what day would work best for you? Because I know you have your exam on Wednesday. And then the best way to do that session is like attempt the worksheets yourself, start the problems that you're confused with the most. So then I could go over those problems during the session and create similar problems to that, to those problems that you make, and then we could go through it on that session.
Okay.
Yeah.
Let me see. So I'm thinking I can be able to do the video by next weekend.
Yeah, like by next weekend. So then when I receive the video, we can do that session on that weekend, on the next
Okay.
weekend. Right.
Okay.
Okay. Sounds good, Janaya.
Okay, thank you. So you do one-on-one sessions like this format and then
I do one-on-one sessions this format. I
Mhm.
also have a 10 session package, which
Mhm.
is like discounted for like $48 an
Mhm.
hour, but it's gonna be upfront like
Mhm.
$480.
Mhm.
I have office hours Tuesday and Thursday nights from like 9 to
Mhm.
11 p.m. like
Mhm.
every week. Um,
Mhm.
but that's gonna be like $20 a month, and you could cancel anytime you want,
Mhm.
like when you're done with the class.
Mhm.
So that is gonna be like you could like spend a lot of time with me if there's like no one
Mhm.
else there.
Mhm.
And the school I usually teach is UC Davis because that's the school I went to and that's where I started
Okay.
from. And they're in break right now, so like it's perfect time for you because
Oh.
like there's gonna be no one else there. So then if you like join those office hours, you're gonna get like 4
Mhm.
hours a week with me, Tuesdays and Thursdays,
Oh,
for
nice. Cause
$20 a month. Yeah.
UC Davis, is that what side of town is that, or like where is that
Mhm.
at on?
California, it's you know by Sacramento. Sacramento
Oh, so
is
you're
right by there.
yeah. So your time zone, you're 3 hours ahead or behind us.
Oh, you guys are
Yep.
3 hours ahead, right?
Yep.
Like New York time,
Mhm.
right? You guys are New York
Yep.
time?
It's 5:35 right now
Yeah,
where I'm
yeah.
at. Yeah.
Right. But when you scheduled it on the Calendly, it like adjusted to your time, right? Adjusted
Okay.
to
Yes,
right,
it
yeah.
did.
And on the Calendly, like I put this week and next week as unavailable because I have exams, final exams coming
Mhm.
up for me,
Okay.
like lab
Oh,
practical
wow.
exams and then lecture finals next week. But I'll make an
Mhm.
exception for you for that free
Oh,
session
okay.
this
Thank you
weekend.
so much.
Yes, of course, of
Okay.
course.
Thank you. So then I will get, you said 30 to 60
Mhm.
video
Second.
second. Okay.
Yeah, 30 to 60
For
second video.
okay.
Testimonial. And if you want some examples, you could follow me on
Mhm.
Instagram and then see like
Mhm.
the other videos testimonials there and I'll follow you
Okay.
back. Yeah.
Okay.
Uh-huh.
Okay.
Yeah.
Thank you so much for your
Mhm.
help. And you go by Brian, right?
Yes, I go by Bryant. Bryant.
Brent.
Right,
Okay.
Bryant. Yeah.
Okay.
Like Kobe Bryant.
Oh, okay. Okay.
Right.
All right. Thank you so much for
Yeah.
your help today because it
hmm
really did help me understand the
Yes.
material better.
And of course, like I hope it also helps you like think about how to approach these problems, how to study for these
Mhm.
problems efficiently, and
Mhm.
not get lost, because I want to like
Yeah.
make sure you're gonna be ready
Mhm.
for the exam.
Yeah.
Right.
Well, I yes.
Yeah. Right. Okay. I'll see you tonight. We'll text.
Okay.
We'll text.
Okay. I'll see you later. Thank you.
Yeah. See you later.
Bye.
Bye.